So here we're going to start talking about our next unit, which is all about quadratic relations, also known as conic sections. So in this video, we're just going to take a look at what those actually look like, and in future videos, we'll look at each one individually. So we've already talked about quadratic functions, and that's where you have some equation, y equals something x squared plus something bx plus some constant. The idea of a quadratic relation is, well, the difference between a relation and a function is that a relation is not necessarily a function. And so what makes something quadratic? Well, we think back to our definitions of polynomials, and all that it takes for something to be quadratic is that the number of variable factors in each term is no greater than 2. So we've seen before, we have something x squared, and there'll be some coefficient in front. I'm just being lazy right now. Plus there's an x term in there somewhere, and then we have that constant term. I'm calling it constant because I'm going to not use it c again. But if there's an x squared term there, there could also be a y squared term, because that's still second degree, we would say. Second degree. And so is this one, the x squared, that's second degree. We also have, let's see, there could be 2 x's, 2 y's. There could also be an x and a y. So this would be x to the first, y to the first. I'll write that in just so it's super clear. This would still be a second degree term. And I don't think there's any other way we could get, again, a second degree term, because remember, second degree sounds weird. That's quad, but second degree does imply quadratic, or that's what we label it. So just like there's x squared, there could be a y squared, there could be 1x and 1y, and then there could be just 1x, which would be a first degree. Oops. Let's use purple there. This would be first. There could just be some y term as well. And then there's a constant again. So these are our first, and then this constant would be 0th degree. And then that would equal something. Usually it would equal some constant, but just it's nice to have everything on one side and then it equals 0. So a general form for your quadratic relation would be something x squared plus something y squared plus something xy plus something else x plus something y plus some constant equals 0. Okay, I just looked back. I was wondering why I got to G, because there should be only 6 terms, but it's because I forgot D. So let's just kind of fix that here. D, F, G. Okay, so that's a quadratic relation. The ones that we're going to look at in this case, or sorry, for the next couple videos, are going to be a case where the C term, the CXY term, is going to be equal to 0. And the reason that is because that XY term right there actually makes the graphs really funky. And at least when we're getting started, I don't want that added level of complication. So most of the cases, that's going to be 0. So the question now is, okay, these are quadratic relations, or the equations of quadratic relations. How does that relate to this idea of conic sections I've mentioned at the beginning of the video? So what do we mean by conic sections? Sections. And to think about this, I want to give you a task. And that task is to pretend that you have 2 ice cream cones and they're symmetric, and you put them tip to tip, one right above the other. So I'll try to draw this. But I did find a nice handy website to help us visualize, but I can't pass up a drawing challenge. Now you imagine you have a sheet of paper of some kind, or a plane, and you're going to slice through that cone, or the 2 cones. What does the intersection look like? And there's a number of ways you could do this. So I'm going to give you a minute to pause the video here and just think about what could happen. Okay, now that you've attempted and maybe tried to draw, if you tried to draw it, I'm very proud of you. But I think maybe the first one that jumps to mind would be if the plane just slices through these cones. And if the cone is, pretend, standing on your desk right here, then let's just say that the plane is parallel to the plane of the desk. What would that look like? Well, since the cone, I should emphasize that the cone is a circular cone. So this base down here is a circle. If I slice through it right here, there, then that cross section, as we would say, basically where the cone is being sliced, is actually a circle as well. It is going to be a smaller circle there. So I'm going to draw this red cross section right here. So that is a circle. And that is what we would call a conic section. So the conic sections are where you have a double cone, and what possibilities could you get by slicing through it with a plane? So one of them is a circle. Now you could see, I think, that if you change the angle of the plane or change the position of it, you're going to get slightly different results. And I could keep trying to draw, but for the sake of time, let's just go to a program that I found online. Okay, so we have this website here, and GeoGebra, and I'm going to link it in the description of the video so you can play around with it yourself. Now, how do I use this tool? Let's take a look. So here's obviously the visual of what you're seeing, and this is what we already had. So I have my double ice cream cone thing standing on my desk, and the plane is parallel to that. So if you go over here, and there's a little shortcut here to tell you the answers, but don't look at that. In this plane, so if you change angle alpha, the blue slider, that will change the width of the cone. This part doesn't really matter too much, so I'm just going to leave it here at 45 thereabouts. If you look at beta, B, that's going to change the angle of the plane. So if I change this angle here, let's switch this way. If I change the angle, it will make the plane more vertical or more horizontal. So right now, this is where I'm at. When B is beta, so beta is right now 90 degrees, and you can see where that angle is right here. If this is 90 degrees, then it would be parallel to the desk if there was a desk here. So what could happen? Well, if I even change the angle a little bit, notice here that the little circle is not going to be a circle anymore. It's going to get stretched a little bit. And so if I change that angle enough, it becomes a little more clear. Oops, let's try this. You can see here that it's a little oval, or an ellipse now, as we would say. And so that's another one of the conic sections. So if the plane is parallel to the bottom of the cone, or you can say the base of the cone, then it would be a circle, the intersection. But if you change the angle even just a little bit, we can notice that this circle is getting stretched, more oblong, and it becomes an ellipse. We might be able to see this better if I change the angle here of the cone, make it a little narrower so we have more room to play with. And now you can see, I think it's a little more clear that this actually is an ellipse. What else could happen? We might notice here, well, there's a reason that there's two cones there that must play into something. And so let's put this back to 45. You can see here, so I start off as a circle, it gets stretched and stretched and stretched until what's happening here? Well, at some point, the plane, you see the blue line over here, essentially from the side view, that plane, at some point, it's going to be parallel to the side of the cone. Or the cones, rather, plural. In which case, hey, it's not going to chop through this bottom one, but it is going to chop through or slice through this upper part of the cone. And similarly, oh, sorry, I forgot to mention, you could also raise and lower the plane with this slider down here. So I could also have it through the bottom one, not through the top one, and so on. But no matter what happens, I didn't change the angle of the plane, I'm just raising it and lowering it. What's happening is that it's always a parabola, it looks like. And hey, we've seen that before. And so the other conic section, or the third one I guess now, is a parabola. You could kind of maybe see what's going on. If I increase the angle now, make it steeper, the angle of the plane that is, make it steeper, it's eventually going to intersect both cones. And what's going on is we got this kind of parabola looking thing up top and this other kind of parabola looking thing on the bottom. And I don't know if you can really tell, but they actually look pretty symmetric. And so that is our fourth? yeah, fourth and final conic section, which is the hyperbola. So let's drop them in the list and then draw little graphs of them. So you have a circle, which is, I'll try to make that a little better. Ooh. I'm going to cheat here. You got the circle. Wait. There we go. And then we have the ellipse, which is essentially an oval, a stretched out circle. I don't know if this is going to make it. Yeah, there we go. And then we have the parabola. So the parabola, which we know and love, looks like that. But notice also, since we're talking about relations, I could also end up with horizontal parabolas like that. That's totally a possibility. And then our last one is a hyperbola. And that hyperbola looks like this on the graph. So maybe I should put axes on here. So maybe this is our axis right there. That could be one right there. Or something like that. You could also have a hyperbola going the other way. And we'll talk about how the equation affects that when we get to hyperbolas. So these are the conic sections, and each of these has an equation that looks something like this. It's a quadratic relation. Now, you might anticipate, like, if you had trouble with quadratics before, this might be a little bit challenging. And so in the next video, or in the future, something we're going to want to be really good at is completing the square. So in the next video, I'm going to take a quick detour and do a little review on how to complete the square.